Welcome, Mindsetters, on this wonderful Tuesday afternoon. My name is Tara, and I am here today with John. Hello, John.
Hi, Tara. Great to be with you, and great to be with you too this afternoon. We're really excited because today is our last session of our normal Learn Extra live broadcasts for grade 10. But we've got more in store for you. Today we're focusing on energy calculations, and I always enjoy those, Tara.
Yeah, definitely. I remember from high school, I enjoyed it. It's such easy marks if you know what to do. So this is so important to get a good understanding of. But before we get started, I want to remind you guys of this really cool competition that's going on at the moment. It's called the Get Connected competition. And entering gives you the opportunity to win a Sony Xperia cell phone or airtime. And the competition ends soon, so you better get going with that. What you have to do, it's quite simple. We've posted the links on our Facebook page, and you have to follow the bit.ly link that we've put up for you that takes you to the Kira page where you must enter. There's a password here that's learn. And once you've entered that, you must choose your favorite Learn Extra teacher, anyone you like. And once you've done that, you come back to the page to the Facebook page where we've posted the links, and then you have to like. You'll see that there's the links for all your favorite teachers. You choose the one that you like the most, and then you share. You share, and you get as many likes, and that gets you into this wonderful competition. It's such a cool opportunity, and it's so simple. So definitely get onto it. You've got until Thursday, so let's see you there.
And you know what, Tara? The other thing is that your winning teacher, the top two teachers, get a prize as well.
So wonderful.
Isn't that a way to reward them for all their hard work? So go and look for the teacher that you like most, and even if you don't enter the competition, you say, I've got a cell phone, I don't want to get airtime. Well, then go and like the teacher that you think is really cool and get them to win a prize. And they'll probably get a prize that will go to their schools as well, and will be something really quite useful. But let's get straight into today's lesson. We're dealing with energy calculations. Okay, so last week we started off with talking about different types of energy. Tracy was here to explain to you how that energy, it's quite a strange thing, you know, and we don't always really understand where it comes from. But it's part of our everyday life. You need energy to get going. You need energy to study. You need energy to do a sport or something. In terms of science, though, we really talk about two types of energy. That which is called potential energy. And in our context, the problems we're going to be dealing with is gravitational potential energy. Energy due to something's position. And then we talk about kinetic energy. Now, kinetic, biokineticist, kinesthetic learner, kine, all deals with something that's a derivative of the Greek word kine. It means cinema as well, moving picture. And energy of motion is kinetic energy. Now, when we add those two together, we get mechanical energy. But we'll talk a little bit more about that in a little while. For the moment, let's see what we're going to do. So, in this lesson, we're going to do the following things. We're going to, first of all, we're going to use a gravitational potential energy and kinetic energy to calculate the mechanical energy of different objects. So we explained what those are. Potential energy, gravitational potential energy, kinetic energy, and now this word mechanical energy. Very important word. Now guys, I know you're only in grade 10 at the moment, but I want to tell you a little secret. That this section carries through all the way through to grade 12. And some people even would say that some of the calculations that you're learning now in the matric exam paper are some of the more difficult physics questions you can get asked. So make sure you've got the foundation now. Make sure you understand this. And then you know what, when you come to the grade 12 work, you'll see it's easy, it's straightforward, and you won't have a problem. Okay, the next part that we need to do is to state and apply the law of conservation of mechanical energy. Now, that word conservation doesn't mean we're going to save the rhinos. Yes, we must save the rhinos. Understand that. Yeah, get on board. Do what you can to save the rhinos. But conservation in this term doesn't mean that we all become gamekeepers or we become conservationists. Okay? Conservation in the physics term means that something remains constant. So conservation of mechanical energy means that in a particular situation, the mechanical energy at the start, the mechanical energy into the process, the mechanical energy halfway through the process, the mechanical energy almost at the end, the mechanical energy at the end will all be the same. It doesn't change. Now that's quite interesting. You've come across in grade 10 some other laws of conservation. So the conservation of mass in chemistry, where we say if we have a certain mass of reactants, we add them together and we do something, then the stuff that we're left over with at the end must be the same mass. Conservation. What I have at the beginning, I have at the end, and I have all the way through as well. Can't lose anything. Conservation of atoms. We start with a certain number of atoms, we're going to end with a certain number of atoms. Even if they don't all react, in a container, we're going to have a conservation of mass and of atoms. Those are just two laws of conservation. There are many other laws. Conservation of charge is one last that I'd just like to mention. So if we have a system, a closed system, the number of electrons and the number of protons in that system will be the same. When we know that they'll be equal. And whatever we do, if we rub with a cloth and we make something charged, conservation of charge tells us that the same number of electrons, same number of protons will always be present within that particular environment. Okay, now having said that, what we are going to also look at, we're going to consider some scenarios when mechanical energy is not conserved. So there are often situations, everyday situations, where mechanical energy is conserved. But there are also many everyday situations where mechanical energy is not conserved. However, what I want you to understand is total energy, not just mechanical energy, is always conserved. So whatever we start with in terms of energy, we'll be able to account for it, a bit like an accounting equation. We'll be able to say, so much goes to potential, so much goes to kinetic, and so much goes to what we would call the work done by non-conservative forces. So that's the idea that I want you to get in your head. Sometimes there are things that happen that take away from our useful energy. And those things include things like friction. Friction isn't very nice to us. But you know what? We couldn't live without it. Because even for me to walk across the floor, I need friction. Because the friction between my foot, the sole of my foot and the floor helps me to propel myself forward. If we were all frictionist, we wouldn't be able to do those sort of things. So friction is important, and sometimes it's important for us to understand that when there's energy that people say is lost, it's not really lost, it's just not transferred or transformed into a useful form. Okay, so I think I've said quite a bit about that introduction, and I'd like to take you straight away to the challenge question. Now, Tara, this is on the page, isn't it?
Yes, it's been posted, so you can find it on our Facebook page.
And I would really like you to have a look at that and see if you can give us an answer as a comment on the page. Okay, so let's read it. It isn't a straightforward question, but I think it is one that will help you understand this idea. It tells us that we have a ball of mass 714 grams, and it's allowed to fall freely from rest from a height of 5 meters above the ground. At what height above the ground will the kinetic energy of the ball be double its gravitational potential energy? That's quite a problem. That's quite a challenge. Now, I hope you enjoy it, because it was something that I sucked out of my head, and I'm sure that you'll find a challenge in it. So let's just recap very quickly. These notes, by the way, you can get. They're on our website, but there's a short link to these notes that you can either download or you can view if you've got a feature phone, and that link is available on the Facebook page. So make sure you get the notes, go and revise, We're heading towards exam time. So it's really important that you do some revision as well. Okay, so mechanical energy, I think I've said enough about mechanical energy. It's just the sum of potential energy and kinetic energy. Notice that the units are joules. And here is a very important statement. Energy is a scalar quantity. Now remember, we've been harping on about vector quantities like velocity and acceleration and change in position or displacement and force. Those are all vector quantities because they have direction. Here we've got something called energy, and it's a scalar quantity. It has no direction. Now, the next one, gravitational potential energy, can usually be written as EP. Some textbooks will have it as U. Gravitational potential energy is the energy that an object possesses as a result of its position in a gravitational field. So whether something is above the floor, a meter above the floor, or 2 meters above the floor, or 5 meters above the floor, it has energy because something's had to do work against the gravitational field to get it there. Okay? Once that there's been energy transferred, oh, you hear my knees creaking, by me lifting something up, I'm actually giving it some energy because I've had to do something to move it through a distance against the gravitational field. Remember, gravity exerts a force downwards, but if I'm lifting something, I'm exerting a force upwards, and I'm overcoming the gravitational field. So in that sense, that's why it has energy, because there's a relationship between work done, which you'll learn about in later grades, and energy. For the moment, we just think about it. I'm putting effort into changing an object's position in the gravitational field. Now, what's very important there is that if I move something from this position at the same height, I'm not really imparting any more gravitational potential to it because it's at the same height. Everything that's the same height above a reference point, like the floor or the surface of the earth, that will have the same gravitational potential. Got it? Make sure you've got that. So there would be no difference between two objects, the same mass, the same height above the earth. Even if they weren't in the same position, but they're in the same relative position, they have the same gravitational potential energy. Next, let's just go over one thing before we move on. What do these symbols mean? Remember, the M stands for mass, and mass is measured in kilograms. The SI unit for mass is kilograms. The G here is the acceleration due to gravity, which is a constant. It is 9,8 meters per second, and it always acts downwards. That's a vector, so we must put the direction in. And H stands for height. And height is a distance measurement, and it's measured in meters. So there are a couple of things when you're using this equation you need to be very careful about. You must use the right SI units, and you must make sure that you use the right value for G, 9,8 meters per second. Right, kinetic energy. Let's move on to this. Kinetic energy is the energy due to movement. And so we call it kinetic energy. Here, the M is again mass, measured in kilograms. The V is velocity or speed. It's actually the instantaneous speed, which could be instantaneous velocity. Doesn't have to have direction with it, and that's why I've called it speed at this point, but it must be measured in meters per second. Now, guys, the thing that I need you to pay careful attention to in this particular equation, whenever you're calculating using kinetic energy formula, what you need to take note of is that the V is squared. So many learners write down the right equation, but when they come to substitute, they forget to square. Okay, so please don't fall into that trap. And then the last thing that we should say is the total mechanical energy of an object remains the same in a closed system. A closed system means that there are no external forces. And an external force is one like friction. It will be a braking force that will slow something down. Now, you know that if you're moving along in a car and you put on the brakes push against the drum, slow down the car, and it gets hot. And you can actually feel the heat in the tires, you can feel the heat in the pads. That is a change of energy, but it's not useful energy anymore. So it's wasted energy. It's been used up because of a frictional force. It's an external force. It's taking away from our useful energy, our mechanical energy. And so we'll come to some more examples of that where there's non-useful energy, and we call that non-conservative forces. Not because they're taking away from our... imagine you've got a pie and we want to make sure that we're going to share it out equally. We want to make sure everyone gets an equal share. And here comes friction along and steals some of the pie. We've no longer got the same amount of energy. That's very sad. But that's the way life is, and it just runs out, unfortunately. And that's just what's happened to me. Time's run out. So, Tara, have you got anything to tell us?
Yes, I do. I loved grade 10. It was such a wonderful year of learning and so many things to look forward to. Now it's nearing the end of the year, and a lot of you are going to turn 17 soon and looking into doing your learner's license, which is such exciting stuff. And I would suggest this wonderful book, The Safeways K53. And what's awesome about this is that you can prepare ahead of time if you're still 16 for your learners, and by purchasing this book or downloading the app on the Samsung Galaxy App Store or the Google Play Store, you can enter a competition to win a Chevy Spark, your first car, before even getting your driver. Sounds like a wonderful plan to me. So definitely, if you're thinking about doing that, get onto that. It's the Safeways K53 Learner Driver book.
And the Google app, the Play Store app, has just been released, and it's a special offer at the moment, isn't it?
I believe so.
Absolutely. So guys, make sure you get that app and get driving. Well, no, don't get driving yet, once you've got your license, okay?
Please. Sounds wonderful, and you can get on that and have a good break. We'll see you just now. Hello, Mindsetters, welcome back. We've got a few questions here which we'll get to right away. But before we do, I've posted all the links for you to view or download the notes if you'd like to. Very important to keep track while we're going through them. But what I've done as well is you will see that there's a test yourself question. And by testing yourself and following that Kira link, you can, and answering the testing yourself and seeing where you are with your understanding of what we've covered today, you can also enter a competition to win a Casio calculator, which is really, really cool and very, very helpful, particularly for the subject. A lot of calculations, and you don't want to be making any silly mistakes. So test yourself, see how you're doing, a wonderful way to see where you are and what you still need to learn, as well as getting a chance to enter into a wonderful competition.
That's right, Tara. And remember that you're going to get instant feedback. So not only are you going to have to wait around to get your score, we've upgraded the service. So you answer all the questions, submit your answer, and it will tell you exactly what you've got right and wrong. Okay, so that's an important part of doing some revision as well.
Wonderful.
Okay, so the one question from Philo Kumalo asked us about gravitational potential energy and said, why don't we have one height? Now, I think what he's referring to is this idea. And the way that I can explain it is something like this. If that was the surface of the Earth, and let's also add in something. Let's add in a building structure over there. Now, when you're doing these mechanical energy, gravitational energy question, potential energy questions, we can decide anywhere what is zero. So I could decide the top of the hill is 0. And if I lift an object up 5 meters from the top of the hill, okay, then I've made that point my standard, my relative, my 0 point. And I'm just going to say it's relative to that position that I've got a height of 5 meters. But I can't go and say, So in the same way, I could go and say, well, let's make the top of this building 0 as my 0 position. So if anything's above it, say, again, somebody shoots something up and it's 20 meters above that, then it's 20 meters relative to this 0 position. So if that was 0, then this position, which we don't really do at school level, but it would work just fine to say that that position at the bottom of the building is going to be a negative 100 meters if the building was 100 meters high. So it's really, because the earth isn't flat and smooth, there isn't one place that we can take as our 0 position. And so that's why we can't have one height. We have heights measured from different positions. We've got to take a look at where our position is. So, for example, above the floor here, if I was I'm standing on the first floor of the building, and this is at a certain height above the floor. Let's say it's 1.5 meters, 1.6 meters. If I were to stand on the first floor, and do exactly the same thing, the energy that the object has, if it was this pen, the energy, potential energy, gravitational potential energy this pen has, whether I'm standing on the first floor or on the second floor or on the ground floor of the building, it would be the same relative to the 0 position. So this idea that I can choose where the 0 position is another very important idea in science that you're going to come up across in a whole lot of areas. And we're going to it's a way for us to compare things against each other. Does that make sense, Tara?
I think I hope we've answered your
I
question.
hope
It
we've answered
definitely makes sense to me.
Okay.
But if you're unsure, please feel free to ask anyone.
Okay, good, guys. Let's get on to today's questions. And here we've got a question that's been adapted from the exemplar. And what we're saying is that we've got a stationary truck that is 950 kilograms, is at the top of a steep hill when its brakes fail. And it begins to roll down the hill. The vertical height of the hill is 17 meters, and we assume that it experiences no friction as it rolls down the hill. Fortunately, at the bottom of the incline, there is a sand trap, and what we're told here is that the truck experiences friction and slows to a halt, traveling 11 meters into the sand trap. Write down in words the principle of conservation of mechanical energy. And so that's the first question. Guys, before I get to that first question, let's say how are we going to imagine to answer a question like this. Just imagine that this is a question you get in your end of year exam. So you've been given a whole lot of information, and it might just seem a lot of words to you. How are you going to analyze it and take it apart and make sure you get the right answers? Well, there are two things that I like to do. And the first one is I try and extract all the information that is the hidden information. Let me explain to you what I mean. As I'm reading along, I've highlighted the given information, like the 950, but look here, a stationary. Stationary means my initial velocity is 0. So on my question paper, I can even start to write in, I know that the initial velocity, we know that it is a steep hill and that the brakes fail. It rolls down the vertical height. We assume that there's no friction. I've highlighted all of those points. Now, I'm also not very good at words, okay? I can write quite well, but I like to draw pictures. So this is what I would do as I'm going to answer the question. I'm going to go further down, and I'm going to draw a picture. So what we've got is we've got the truck at the top of the hill, steep incline, and I'm now going to start to fill in some of the missing information. We're going to say, there's the truck. We know that it was 500 kilograms. The mass of the truck was 500 kilograms. We know its initial velocity was 0 meters per second. We also know that the vertical height, notice the vertical height from the top of the hill to the bottom of the hill we were told, doesn't matter how steep it is. I've just drawn it really steep. Wouldn't normally be that steep. I'm just exaggerating it. That is a height of 17 meters. So that's my height. And we're told at the end that between this position, which we can call position A, and this position B, that there is no friction. So we can even put in here, the frictional force is equal to 0 newtons. But after this, there is friction. Over here, we know that there's a frictional force. And so much so that it takes 11 meters between that point and that point, 11 meters, until the final velocity of the truck is 0 meters per second. I think I've got all the information in. Let me just do a double check and make sure that we have. So it's that last bit. At the bottom of the incline, there is a sand trap, and that's what we've indicated, where the truck experiences a frictional and slows to a halt. A halt, V final equals 0. 11 meters into the sand trap. And so, yes, we've got it. So I hope you've got that idea. Whenever you get a mechanics question, whether it be work or motion or a vectors question on forces, draw a little sketch. Make sure you've consolidated all your information. That will help you, and you'll see we'll go back to that sketch as we're doing through the different parts of the question. It'll help you unpack and make sure you've got the whole thing. So this is bookwork. Write down in words the principle of conservation of mechanical energy. And all we're going to say is that mechanical energy does not change in a closed system. Now, there are other ways of writing it, but that's a simple statement. Another way would be saying it's impossible to create or destroy energy. It's one of those similar to the conservation of mass. I prefer this one because it's saying in a closed system, it's always going to be the same. And remember what mechanical energy is? It's the sum of potential and kinetic. So now the next part of the question, which is really the calculation bit, it says calculate the gravitational potential energy of the truck at the top. Notice the position just before it starts to roll. So now just before it starts to roll means that there is no velocity, there's no speed, so there's no kinetic energy. So we're only interested in mechanical energy. Look at potential energy, gravitational potential energy. So the important parts that we need to go from this sketch, we need the mass, we need the height, and of course, what's the missing unknown bit? We know that g is 9,8 meters per second, and it's acting downwards, per second, and it's downwards. So we can take that information and let's calculate the potential energy. So EP equals m times g times h. The mass was 500 kilograms. We don't need to put the units in. The acceleration due to gravity, 9,8. Put them in brackets. And then the height was 17. And you've done the physics. You've done the majority of the work. But let's do the calculator now, and we pull up the calculator, and we're going to say, let's take 500 multiplied by 9,8, make sure you're entering correctly, multiplied by a height of 17, and it gives you 83,300. So 83,300 watt. No, don't leave it. What is it? 83,000, don't say watt. No, it's joules. So we must put the unit in. Very important, guys. You've done all that work. You've got to identify what the unit of energy is. And the SI unit of energy is joule. It's not kilojoule, it's not millijoule, it's joule. So unless they've asked you for it, leave it as joule. And so we are going to say it's 83,300 joules. That's the amount of potential energy that this object has. Let's move on. And now have a look at the second part. At some point B, as it's rolling down the hill, it reaches a speed of 13 meters per second. Use the principle of conservation of mechanical energy to calculate the vertical height of point B. Guys, here we've got the rule. We've got to apply the rule. And it's very straightforward. What we know is the following. The mechanical energy at the top is going to be equal to the potential energy plus the kinetic energy. And let's just make sure that we've got this clearly set out for our examiner. We know that that one was 83,300, but we must tell them that kinetic energy, and I would probably need to do this on a separate line, but I'm just going to remind you that it's half mv squared, and that in this case v equals 0, so the kinetic energy is 0. Now I haven't set that out very well, but I hope you'll understand, and that you won't set it out like this, but you'll set it out properly with all the bits and pieces showing that substitution of 0 for the kinetic energy. You've got to show the kinetic energy being 0. Calculate it. Now, if that's the case, what do we know from the law of conservation of mechanical energy is that's also the mechanical energy at any point in the journey. So it is the same. It doesn't change. It stays constant. And so therefore, it will be the total mechanical energy at B as well. Got that? You must make sure that you've got this statement and it's set out very clearly. So we know that the total mechanical energy at point B is the same amount. Now, just to give us some space, I'm going to erase that and put that like that, and I'm going to indicate this is equal to E mech at point B, which is equal to 83,300 joules. Now, what we were told is that at point B, what do we know? We know that the kinetic energy, well, we know that the object has a certain speed. It has a speed of 13 meters per second. So let's work out the kinetic energy. And we're going to say EK is equal to half m times v squared, which is equal to half times the mass, which is 500, times 13 squared. Don't forget to do the squaring. So let's get the calculator up again, and let's understand what that is. We're going to say half 0,5 times 500 times 13, and I'm going to square the 13 and check that I can see on the calculator screen that there is a square there. So that tells me that the mechanical energy, or the kinetic energy, is 42,250. 42,250 joules. So guys, what we notice is, here's the statement. The mechanical energy, E mech at B is equal to the kinetic energy at B plus the potential energy at B. And for the moment, what we know is this was 83,300. We know that we've just calculated this one, and it's there, 42,250. But we don't know the potential energy, EP at B. We don't know it yet. So how are we going to work it out? Well, it's not too difficult. What we're going to do is we're going to subtract the kinetic energy from the mechanical energy, and let's just go and do that, and we can then get the potential energy. So we're going to say 42,250. Let's clear that, and let's go to our 83300 minus 42,250, and this will give us our potential energy. So it's 41,050. Our EP at B is 41,050. I think, let's just double check, and 50, correct? Joules. But now what do we know about our EP? Our EP is equal to mgh. Have I answered the question yet, by the way? No. What was the question? Calculate the vertical height at point B. So again, I'm going to need to do some erasing here because I've run out of a little bit of space issue here. So I'm going to keep the information in my head, and we're just going to make sure that we've got it. So we know now that EP was that value of 41,050, and we know that EP equals mgh, which is equal to the mass of the vehicle. That was EP, 41,050, and this was 500. This was 9,8. This was H, equals 41,050. Now, how do we find H? Well, guys, it's not difficult. What are we going to do? We're going to divide this 41,050 by the 500 and divide it by the 9,8. Or we could say 500 multiplied by 5,8, and we could, 500 multiplied by 9,8, and then divide that. But I'm just going to do the division, divided by, and I'm going to put it in brackets, 500 times 9,8, and I think that's the easiest way to do it. And we're going to get an answer that the height is 8,377. Round off to 2 decimal places, 8,38. So final step, my height is therefore my height is 8,38 meters. Sure. Hope you've got that. No, we're out of time. Tara, you've got something to say.
Yes, I do. I have something very interesting to tell you guys about. It's this exciting event that's taking place this weekend. I'm dying to let you know. So it's on the 25th and the 26th of October. That's Saturday and Sunday of this week. At the Kyalami racetrack, Shell is hosting this eco-marathon where they're calling students from all over the country to design and build and run and test
and compete.
Compete and develop the most fuel efficient or energy efficient vehicles, or whatever, mainly vehicles it would be. And it sounds absolutely incredible to think, here we are entering competitions to win a Chevy Spark when you could be creating your own energy efficient car, which I think is absolutely amazing.
And it's going to be amazing to see. This is an international competition, and it's been run all over the world. This is the first time it's come to South Africa. So you're in grade 10 now. Maybe come along if you're in the Gauteng area, get some ideas, and you could enter for next year's competition because it's going to be ongoing.
It sounds absolutely incredible. So it would be lovely to see you there. I think you'll learn so much, and maybe you even get to try out some of your own ideas to the aspiring science students there.
Science and engineering. Okay. And guys, the entrance is free, so you don't have to worry, but bring a backpack, bring sunscreen, come along and enjoy the day. Okay.
Definitely. Let's take a break and we'll see you straight afterwards. Hello, Mindsetters. So we've got a lot to do in a little bit of time, but I have to tell you about a very important notification. We've enjoyed having you with us throughout the whole year during this time slot, learning new things for various subjects for the grade 10s. But from next week, Monday at 5 p.m., we're going to start exam revision, which is so crucial and it'll be so helpful and important for you to attend. To come watch us and see what we cover. We'll put up all the schedules and all the time slots and what subjects we'll be covering during those times for you to see so that you don't miss out. We won't only be covering maths and science, but as well as things like geography and accounting, I believe.
And maths literacy.
And maths literacy. So we're going to be doing it all. Make sure that you use that time effectively and come see us. We've also got a few questions, John, just before we get to you.
Okay, let's go for it.
The first question, a lot of you wanted to know if we had to convert the kilograms to grams for this question that we just did.
Okay, so guys, please remember, this is very, 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 very important. For physics, the SI unit for mass is kilograms. Okay? For SI unit for mass is kilograms, and we'll see that in the challenge question. But for our truck question, we can't convert it to grams. Well, it doesn't make sense. It's very important as well to notice in chemistry, then we convert from kilograms to grams. So SI units for mass when we're dealing with physics, kilograms, SI unit. When we're dealing with solutions and chemistry, then we use grams. Okay.
Makes sense. And one more question from Thato. He wants to know if he would be wrong in saying if the law of conservation of energy is that charge cannot be created or destroyed but transferred from one object to the other.
Okay, Tara, that's a very common misconception. It's wrong. Sorry, Tato, but you're going to have to learn that when we deal with mass, it's not a change in charge. Conservation of mass and conservation of energy and conservation of charge are three different laws. And when we're conserving mass or conserving atoms. When we're conserving charge, we say charge is conserved. When we're conserving energy, we must say the total mechanical energy remains the same. It's not destroyed, it can't be created, but it can be transferred or transformed into different forms. Okay, so I hope you've got that, but please be very careful. Don't confuse mass, charge, and energy. They're not the same. They're very different things, although they are related, but that's a topic for another day with Dr. Einstein and his E equals mc squared. We're not going to do that today. Okay, so I want to just finish this question very quickly, and then I'm going to we'll go to the challenge question. So let's go here. It says, calculate the velocity of the truck, and I might not get all of this done. The velocity of the truck when it reaches the bottom of the hill. So guys, here we're doing exactly the same thing. We know that the total mechanical energy at the top of the hill was equal to 83,300 joules. So what do we know about the mechanical energy at the bottom, at the start of the sand trap? We've said it, at the point B all the way through. It's still 83,300. Now, what do we know at the bottom? We know that at the bottom, EP plus EK is going to be equal to 83,300. But what do we know about EP? At this position, at the bottom, and look, there's the diagram. Down here, B was somewhere there. I missed that. That was C. EP here is 0. And what we're recognizing is that means mgh plus half mv squared. We're going to put in the mass of the truck, 500, times g, 9,8, times height, which is 0, plus half m500, times the v squared, which we are trying to find. We don't know what the velocity is. So what are we going to do? We're going to recognize that this one comes to 0, and over here we've got 83,300, and so we're going to take our calculators and we're going to work out v squared. Now look what I'm going to do. I'm going to take 83,300, I'm going to divide that by a half times 500, and I should get my answer. So in fact, you know what I'm going to do is I'm going to just put it onto my calculator and let's see what we can do. We're going to say 83,300, delete that last one, 300, divided by the half times 500, and close off my brackets. That's what my velocity squared will be. So what I'm now going to do is I'm going to take the square root of that. Don't even need to find that. And I'm going to push the answer. And I'm going to find my answer is the velocity at the bottom is going to be 18,25 meters per second. 18,25 meters per second. And that's my velocity before it hits the sand trap. Very important. Guys, that's going quite quickly. How would we convert that to kilometers per hour? Very last question that I'm going to do here. We'd multiply by 3,6. and you'll see it's going 65,71 kilometers per hour. It's still quite fast for a truck that's probably out of control. Okay, challenge question time. Let's go there. And we're going to go straight to the bottom, and there's our challenge question. Great. And very quickly here, Tara, might be where they were referring to changing grams to kilograms.
I believe so.
It might have been there. So yes, guys, you've got to change the grams to kilograms here. And so make sure that you've got it. You've got that the mass is going to be 0,714 kilograms, that that G is 9,8, and we know that the height is 5. So I'm going to do it very quickly. I'm going to say EMEC at the top is equal to, I need to find my EMEC. So it's EP plus EK at the top, and I would substitute in, and I'm going to just do it on the calculator and work those out. So clear the calculator, and very quickly, now we do 7.4 times, that was the mass, times 9,8 times 5. And that's my total EP. Let's write it down. 34,986. 34,986. 34,986 joules. Now, guys, I didn't work out kinetic energy because we know it's 0. So I was just taking a shortcut. The next part of the question is the real thinking part, though. So I really want you to work with me here. It says, at what height above the ground will the kinetic energy of the ball be double its gravitational potential energy? So here, this is what we're going to say. Let EK equal, remember, it's 2 times a certain amount, and EP equal X. So if EP is X, then EK would be 2X. That means that M mechanical, EMEC, is going to be equal to 2X plus X, which gives me 3X. Are you with me so far? I hope you are. Now, guys, to work out the X, the EP, all I'm going to do is I'm going to say, if I know that this value here is my total, which is 34,986. 34,986 is going to be divided by 3. That will give me my EP. Okay, and so quickly onto the calculator, 34 divided by 3 gives me an amount that tells me that the EP is 11,6. Oh, what was that?
662.
662. 11,662 joules. Now, am I done? I'm almost done. What have I got to do? The next thing I've got to do is I've got to say, I know that EP equals mgh. And if you look at the question, it asks for me what height. I need to find h, and I know that I'm almost out of time. So I know that's 11,66. I know that that mass is 0,712. I know that g is 9, there we go, and h. If I do the calculation, I can find out what h is. The answer is posted on the page.
Sure. Thank you very much for joining us today, guys. We had so much fun with you, and I'm so glad to see so many of you had questions you want to know and you want to understand. It's great. Such a great section to learn about, and it's very good for you to have a thorough understanding of it. Don't forget about all the competitions that we've got going, and to join us on Saturday at Kyalami Racetrack for some awesome fun. And Monday next week at 5 is exam revision. So much to remember, but we'll see you soon. Bye, Mindsetters.